I'll be talking on federated graph neural network framework for real-time anomaly detection in distributed cloud system. 2 points there, real-time. Now the next one is federated. Okay, so let's move on. As a way of introduction, it's no longer news that we've moved from industrial society into an information society, whereby every aspect of human activity has an evolving technology. We are no longer where we used to be. Yeah, for example, now I can remember there were times to do money transfer. I think you have to wait for 5 or 7 working days before it will reflect in the other person's accounts and so on, and so many stuffs like that. But now we have an evolving technology that has changed that. So evolving technology has a great impact on critical infrastructure system, and cloud computing is an area under critical infrastructure system. So what is cloud computing? Cloud computing is just a pool of shared resources over the internet that requires minimum management of the cloud providers. However, cloud computing, as nice, as awesome, as promising as cloud computing is, it has some disadvantages such as vendor lock-in, scalability issue, resource contention, and so on and so forth. In a bid to solve limitations we have with cloud computing, federated cloud was developed. What is federated cloud? Federated cloud is a voluntary pooling of cloud computing, cloud providers, under a federation or under a federated law. There is something. So under cloud computing, we have what we refer to as SLA, that's service level agreements. But when you come into federated cloud, we have another agreement that kind of supersedes or goes line by line with the SLA. That is FLA, that's federated level agreement. Okay, so here we have the traditional cloud, that's the existing one, the one that had the limitation of vendors locked in, resource contention, and so on and so forth. Then we have the multi-cloud, and then we have the federated cloud. In federated cloud, either single cloud or federated cloud, we have different components that makes up the federation. We have the centers, the data center, where you have your storage, you have your computing, we have the head servers, we have the head devices, the devices that actually make up the federation. Because we were trying to solve the limitation that accompanies a single cloud. So under federation, we have resource sharing. So let's say, for example, we have like 6 clouds that form a federation. Then we have jobs. Yes, it is called job. Yeah, job on a particular cloud, and the cloud is kind of choked. It doesn't have enough capacity to accommodate that. But because that cloud is in a federation, there is no permission needed, yes, before another cloud will be able to take up that work without the customers, the clients, knowing anything that is going on underground. So that is part of the advantages of being in a federation. Then also business integration, we have intelligence distribution, application interoperability. Yeah, but however, there are still some challenges with federated cloud. Federated cloud was able to solve the limitations that has to do with cloud computing, but federated cloud also has its own challenges. One, because of the diverse components that makes up the federation. For example, now the one I'm familiar with, a federated cloud I'm familiar with, the one we have in Covenant University. We have one of the cloud in DRC Congo. We have one in Landmark University Omaro. Then we have one in Afe Babalola in Ado-Ekiti. Okay, so we can imagine the geographical stuff. So there is every likelihood that that cloud will fail. It might be due to security threats. It might be due to component failure. And most times people focus on security threats. People are trying to look for malicious activity. They're trying to see DDoS attack, and they forget the fact that components can actually fail. A particular server can be down, and it will bring down the whole cloud, the whole federation. A particular data center might have issue. It might even be just a single hard disk in that data center. Then you will have system administrator running a tasketer. What could be the point? What could be the cost? So in order to solve this, and also to reduce the time that system administrator use in troubleshooting challenges with federated cloud, that is the main essence of real-time anomaly detection. So when we say real-time anomaly detection, we have different different type of anomaly. We're going to get there. Before the system finally fail, the system administrator should be able to get the alerts, and not just get alerts. They should know where the problem is coming from. So I just don't want to sit and just get, there is a problem. Where is the problem coming from? Which component exactly is bringing that component before the whole system will fail? Please go back. So we have several works that are because of how sensitive this is. Then also because the data, we have billions of data being generated on a daily basis from clouds, then from federated cloud. Then a lot of work has been done on real-time anomaly detection. But like I said, what's most work focused on is what I refer to as binary classification. That means they only classify there is an anomaly and there is no anomaly. They actually do not go into details to the type of anomaly we have. So what are anomalies? I would say an anomaly is an observation that deviates so much from other observation with the suspicion that it was created by another mechanism. So we have different type of anomaly. We have statistical anomaly. We have contextual anomaly that has to do with time. That means if the time is not, for example, yes, if you have like we expect that in the finance sector now, we expect that maybe big transactions should occur in the daytime, but when you're seeing such transaction in maybe 3 a.m. odd hours, it's not because big transaction is an anomaly, but because of the time that it occurred. That place it as an anomaly. That is what we refer to as contextual anomaly. Then we have collective anomaly. That is an anomaly that it is not an anomaly when it's on its own, but when it is in a particular group, then it becomes an anomaly. Yes, so this is the taxonomy of the anomalies. Like I said, we are not just detecting the anomaly. We want to see the hierarchy of the anomaly. We want to know where the anomaly is coming from. So for example, now we have the level 1 where you detect the infrastructure anomaly, then to the application anomaly, to the business anomaly, to the security anomaly. Yeah, so how do we detect? We've established the fact that anomaly exists, either from security or from performance. How then do we detect these anomalies across distributed system without compromising privacy? Okay, so that leads to, so the evolution, yes, the method have been used for detecting anomaly in cloud. We have the traditional approach. The traditional approach basically just deal with setting rules, setting threshold. So you have rule like when you exceed this threshold, you flag it as an anomaly. That has been the method that has been used before. But we understand that we've passed through that. You can't set rule for ever-growing data. We have a lot of heterogeneous cloud. The rule you set for this particular cloud might not relate to that particular cloud. So that became ineffective. So it's moved to using machine learning, trying to be smart, using machine learning. And the first approach using machine learning can be referred to classical machine learning. Okay, so classical machine learning was able to overcome the challenges with rule-based. It doesn't use rules. Rather, it learns from the pattern of the data to detect anomaly. However, it was discovered that classical machine learning assumes data dependency. Okay, so it treats every data as individual, like they are not related to another. So that brought about a lot of false positive and a lot of issue. So then that led to deep learning. Deep learning has been in use since 2018 to date. So deep learning tried to overcome the challenges with the classical machine learning. Number one, by solving, because classical machine learning became slow at a point when it comes to a lot of data. So deep learning, because it has a lot of layers, hidden layers that can accommodate layer no matter the that can accommodate data no matter the amount of data. Deep learning will be able to accommodate that. So here, like I mentioned, why traditional approaches fail, because rule-based, I already explained this. Yeah, you set rules which is not effective with the ever growing data. And I mentioned something about the classical machine learning. Yeah. So from these statistics, I got this. Like we have there was a record from this money transactions up there. This was in a blog that we had over 200,284 failed e-transaction on this particular day, February 17, 2018. So I probed that further. Why the failed transaction? Fine, there are different things that can cause fake transaction. But let's relate it to what we are dealing with now. Let's relate it to anomalies. So yeah, what could have been the cause? Mind you, every cloud has inbuilt security. There is no cloud system without, in fact, grounded security system. But no matter how ground they are not robust enough. Why? Because the foundation actually depend on data independency, like I said. Okay, for example, like this, then I took a scenario of a colleague that had he was trying to log in to his mobile app. The first attempt, it was network error. The network was not too strong. So the first time, the second time, next time, it was logged out of that mobile app. So I took that scenario. Okay, so that is what I can refer to as like an isolated detection. How we explain. Okay, so because of several attempts, which might have been like an anomaly to that system, it was logged out because an anomaly was detected. But that anomaly was not traced to see why that is coming from. It was just like an isolated detection. That means the only anomaly that was detected that time is several login attempts. They didn't check what could have been the cause. If it were to be hierarchy, like if it were to be connected, they will have seen that, okay, maybe it's poor network, the IP of the network and all of that. It would have prevented that kind of logged out. So let's move on, please. Yes, we have that. That's part of the problem with that traditional approaches for then centralized monitoring. Okay, that's one of the problems that federated cloud tried to solve, because in federation you cannot do centralized monitoring. It has to be decentralized. Please move on. Okay, so when we're talking about graph, why are we using graph for cloud system? Like I said, so we are solving two things now. We are solving the issue of data dependency in in federated cloud, and we're also solving the issue of hierarchy. So number one, we want a system that does not assume data dependency. We want a system that shows the connection of every data. So there is no data that exists on its own that is isolated. So we want a system that will be able to show all that is connected to that. That is why we need a graph. So looking at graph basically normally in its normal state, it has a topology that is interconnected. So that is why we're trying to structure the logs in graph. That will help to show the relationship, underlying relationship within logs. So it will also help in detecting anomalies. Please move on. Okay, so like I said, graph has natural representation. So in graph, when we mention graph, we're basically talking about nodes and edges. Okay, so what is node? For example, now let me move from the education sector to maybe finance now. Okay, so in node, we have the users, we have what we call application logs, we have transaction logs. For example, the application log now, a particular user will be a node. The user ID will be node futures. The user is connected to a transaction. So the transaction is another node. The connection between the user and the transaction is the edge. The edge feature will be perform this transaction. So going to the education sector now, when we have logs from servers, the log is entry, each log entry. So the node can be a particular server. Let's say we have 6 servers. So one server will be a node. What the server is connected to, another node. The connection between them, that's the edge. Then what type of connection is between them? That will be like edge futures. So another example we can look like is publication. When you're writing paper, the author will be the node. The title of the paper is another node. This author wrote this paper. That's the edge, and that is the edge feature. So here, let's move on. So one key advantage of constructing our logs in graph structure is what we refer to as message passing. So this basically helps to solve the challenge of isolated detection. So when we want to detect anomaly using graph data, it doesn't just pick the anomaly from the node. It does what we refer to as message passing. That means looking at the nodes that are connected to that particular node that is looking at that particular time. We refer to them as neighboring nodes. Looking at them, it gets the features from those neighboring nodes, also the edges that are connected to those neighboring nodes, in order to have what we refer to as to reduce the number of false positives. So it doesn't flag something that is not an anomaly, like that heat is an anomaly. Like the example I cited the other time about a colleague, that was not an anomaly, that was a network problem, but it was flagged as an anomaly because there is no connection between the data. Yeah, so that is one thing Graph does. It performs what we refer to as message passing, and in literature, it was discovered that it gave better accuracy when you use Graph to construct. It has produce better accuracy in detecting anomalies. Okay, so we have different type of graphs, graph neural network in literature, but I picked these three major ones. Why? Because they've been extensively used in literature. One is the graph convolution neural network. Yes, that was like the basis of this graph neural network. It tried to mimic what we know as CNN, that's convolutional neural network. But the major problem with graph convolutional neural network is that it performs what we refer to as transductive learning. So it's going to work or perform based on only the data that is trained with, and we know that is not good for a cloud. We have incoming data every time. So we want something that will be, so if we have new data, you have to retrain for graph convolutional network. So we want a model that will take new data and not retrain and still perform well with new data. So that is what GraphSage does. GraphSage performs what we refer to as inductive learning. Then for graph attention, gated attention network, it's helped to overcome the challenges with graph convolutional network. But when we have large data, it becomes very expensive because it's perform recursive learning. Okay, so from logs to graph, how we construct logs to graph, I've stated that already. This is node creation. I just tried to put an example. Let's say we have a VM. We serve as a node. So we have the futures, then we have the timestamp, which are the node futures. They're the futures of that particular node. Yes, please move on, please. Yes. Yeah, I've explained this. The hedge formation, that is the connection between a node, connection between one node to another. That is what we refer to as edge. And so from that edge, we also have edge features. And another thing I should state here is that, like I said, several work has been done in this in literature. So even work that decided to use graph to structure logs, there is something they did because how will I put it now? They dealt with only nodes and edges. They did not consider edge features. So because we do not just want to solve the problem of isolated detection. Like I said earlier, that we're solving two problems. We're solving isolated detection, and we're also solving the problem of hierarchy. Okay, so because we are going further, we are not stopping at binary classification. There is a very need to know the features of the edges. We want to know the type of connection. We just don't want to know, okay, there is a connection between this node and what type of connection. Okay, this user here is performing this transaction. What type of transaction is the user performing? So that is the essence of the edge creation. So going to federated graph neural network now, I think I've established to some extent what graph neural network is. Now bringing it into federated cloud. I mentioned earlier that federated cloud does not perform centralized monitoring. It has to be decentralized. And when you're decentralizing a model or a system, you have to perform what we refer to as federated learning. Federated learning simply means learning from different devices without sharing their data. It's just that simple. Okay, so federated learning, it trains model without sharing raw data. It preserves your privacy and also that is what federated learning does. Okay, so benefits of federated learning, yes, number one, you can train the global model. We have a global model that is deployed on different clouds that made the federation on decentralized. There is always a global model. So we have the model there. Each cloud that makes the federation can take up this model and train on their own site without necessarily sending their data to the global model. Then also secure aggregation, yes, and global model distribution. Okay, yes. So multi-layer privacy protection, yes. So this is the area where we have the hierarchy now. So everything I've been saying since has to do with a single cloud, or has to do with one class. When we have different layers, that means we need to have the same model up then to the next layer, no matter the number of layers we are looking at. But we know that will be computationally expensive. So we have to come up with something that I refer to as multi-layer privacy. So in literature, there has been several security mechanisms that has been employed into federated, because aside from training the global model on their sites, they have to send the updates to the global model. So sending these updates, several things can happen. We can have unauthorized person intercepting the updates that is being said, and that's going to spoil the whole work. So we have different methods different mechanisms that have been used in literature in order to prevent or to preserve the data, the model update that is being sent from the local client to the global client. So one of it is what we refer to as differential privacy. So what this does basically is just to add noise to the updates that is being sent in order to mask the information. Okay, so let's move on. We have homomorphic encryption that has to do with encrypting the data, the update that is being sent. That is referred to as full privacy. Okay, so let's move on. Then we have what we refer to as secure aggregation. So this secure aggregation use what we refer to as secure multi-party protocol. That means the different party try to come together to perform a particular function without sharing their data. So that is what this secure aggregation does. Then straight to the anomaly detection itself. So let's move straight to building the model. We've talked about the fundamentals of the model. So building the model, now the first thing to note is that since the model is graph neural network, the only input it takes is graph data. So we've established how to transform or how to model or how to structure, whatever you want to call it, our logs into graph. That has been established. We already know what logs or what node edges and all of that. Okay, so after that, the graph data now, how does the model seal the graph data? How does it handle new logs? You know, what actually comes into the model is an end-to-end model. It will take logs, log rows. It is the work of the model to structure the log first, because logs are generally in their unstructured form. It is the work of the model to structure the log first, transform it into graph before detecting or extracting features that are necessary for the detection, before detecting, then before performing classification. So are we clear on that? Okay, so now when we have new data, new logs coming in, this is what we refer to as dynamic graph updates. Like the model should be able to update the graph data as new log comes in. So one of the methods that has proven to perform well in literature is what I refer to as sliding windows. Okay, so you can set the time, but for this particular work, because this particular work has been done, for this particular work, what I used was 5 minutes sliding window. So what it does is that at the set interval that you put, it might be 1 second, it might be 1 minute. What it does is look for the 5 recent logs that comes in. So it can be from 12:05, because it uses timestamp, right? You know, logs include timestamp. So it can be from 12:05 to 12:10. So it takes that. Then if you set it to be at maybe 1 minute interval, let's say this happened at 11:59. So when it's 12 o'clock again, it looks for another log from 12:06 to 12:11. Okay, so that is what the 5 minutes window sliding does. So for the communication optimization, like I mentioned, that we have the existing federation that I use as a test bed have its cloud located at different places. So how do they send updates without having communication overheads or bottlenecks? So that is what is referred to as a communication optimization. So there are different types of communication optimization that will help to reduce. So with the figures you're seeing here are the results gotten from the work itself. So when we built the model, we discovered that the bandwidth reduced by this %. Then the compression rates, so what the asynchronous updates just means that the cloud do not send their updates at the same time based on set rules. It might be because of, so the rules that we basically use was, okay, so for this particular for this particular cloud, how often does the accuracy change? Okay, for a particular cloud that has an accuracy of 98 the first time, the next time 98.1, and another cloud that has the accuracy of maybe 86 the first time, and another time 96, we want to consider that one to send updates first. So that's part of what we use for for the asynchronous update. And another thing that was used is the volume of data that is involved in that particular cloud. So it basically means that all the cloud will not be sending their updates to the global server at the same time. Okay, yes, so I have here work that has been done in federated graph neural network. So it's not like, okay, federated graph is new. No, we have several work that's been done, and I try to put them here. I think there is a slide I put the particular paper where you can read on them. We have the FEDGERTs, we have this, but all this work do not, they only incorporated federation into graph neural network, and they use they use different variants of graph neural network, but they did not perform that hierarchical classification that I'm referring to. Please, let's move on. These are several works that have been done. Okay, so this is just the process flow of the work. The data sources, the data might be from metrics. Why is it not showing? From logs, okay. From logs for metrics, then construct the data. You construct the data from the logs, then the model, that's the GNN model. It trains on each cloud. That's the local graph neural network. It aggregates the model updates, then it performs the detection. Okay, so please move forward. Okay, so when we are talking about the hierarchy now, yes. So we have the data layer, we have the model layer, we have the processing layer, we have the application layer, and several things that are involved in each. So for this particular work, like I mentioned, that the model that was used was GraphSage, then the architecture, then I incorporated what I refer to as hierarchical attention, because I wanted to perform hierarchical classification, and also the temporal graph neural network. That basically has to do with the time, like I explained, with the 5 minutes window sliding. Okay, yes, please move on. Okay, yes, this is just to give us some mathematical foundation about what actually happened behind graph neural network. Like I mentioned, it performed what we refer to as message passing. Then, okay, so what this attention mechanism does is just to enhance the intelligence of the graph. Okay, so it looks at the graph. The graph itself, looks at the node and look at different features in the node. Then try to give attention to the one that has more features. Yeah, it's just that. So yes, I have the mathematical formula for the graph variant that I mentioned before, the graph convolution network that was developed in 2016. Then the graph attention network and others. Okay, so yes, let's move on. Yeah, okay, like I mentioned the other time when I was talking about communication optimization. So several work, yes, like the Fed average algorithm, it was used to reduce communication overhead in federated cloud. Yes, so they use several, they refer to the algorithm, you can name your algorithm whatever you want. They refer to their own algorithm as federated average. Whereas when we try to incorporate this particular algorithm into the hierarchy, it failed because it was developed for flat classification. Also, FedPros. FedPros also was like an advancement over FedAv, but at the same time, it failed also on hierarchy. Then this scaffold algorithm, yes, this scaffold algorithm, we couldn't experiment with it. We couldn't use it because, number one, the algorithm wasn't made public. They just reported that it gave better results than, in fact, the accuracy was not reported. They just noted that it gave several better results than FedPros. Okay, so what was used? I don't think I have it here. What the algorithm that was used for this particular work is what we refer to as layer-wise algorithm. So what layer-wise does is it picked the underlying algorithm from Fed average, then try to incorporate hierarchy into it so that it can suit into our system, since we are going beyond the normal flat classification. So this has been explained before. This is the differential privacy stuff that I explained earlier. The handhole, and that is the noise that is being added to the gradient that is sent to the global stuff. Then making it production ready. What do we need to do to make this beyond the classroom, beyond paper, beyond all of this? We're trying to see how we can bring this to life. So the first thing is the amount of data that is involved. So sending updates can be a bit heavy, a bit huge. So the first thing from literature that I discovered is that to compress the model. something referred to as model compression. So there are basically 3 ways of compressing the model. Number 1 is the quantization. That is like, so you have an update that is like 32 bits long, and not just for a single cloud. So you can imagine if we have like 10,000 clouds. So we have each one with 10,000, that would be too much. So we can perform what we refer to as quantization for that. It's basically without losing any info. It's just to reduce the bits to like 8 bits without losing any information. Then this one, the pruning is trying to look for parameters that are not really necessary, that do not affect the output. Then it removes such parameter. Then that leads to something we refer to as specification. Then the knowledge distillation. Knowledge distillation is like a faster and smarter student trying to learn from the accuracy of the teacher. So the student does not need to learn from the label. It basically learns from the output of the teacher. It's also, I don't know if you're familiar with transfer learning. You do not have to train from you do not have to start from the root. You're basically standing on the shoulders of elders, so to say. Okay, so yes, please move on. Okay, so for the communication efficiency as well, another way is using the top case specification, gradient compression. Then this adaptive synchronization is the same thing as the asynchronous updates, like different clouds send their updates at different time intervals. Okay, yes. So we are talking about, so basically the hierarchical classification is, we can say, is scalable in a way. What I mean by that is we want a situation whereby we train with log from Google Cloud, for example, and we'll be able to deploy that same model on AWS Cloud, giving different hierarchy. So the hierarchy is kind of flexible now. So for example, now this particular model was trained with logs from the federation that I said occur in Covenant University. So basically, we have just 5 hierarchy from that cloud. But when this is deployed on another cloud, it's kind of take up the hierarchy that exists in that logs and produce the exact hierarchy. That it doesn't have to be 5; it might be 4, depending. It can be 6 or more than that. Then we have a publication on that already, IEEE access. Yes, I think we just got a first acceptance from them. Then the accuracy, yes, like I said, the figures are saying, yeah, they are the result gotten from the model. So yes, we're able to get, for the detection rates, we got from 85 because they are different level, and apart from the fact that they are different level, so we did detection rates for each cloud, each contributing cloud, decentralized, centralized, and at different level. So the range is between 85 to, that's supposed to be point, sorry, to 99. Then the precision, the recall, the F1 score. Then yeah, the communication overhead was reduced by 97.6. Then also energy preservation. Yes, okay. So this can be deployed in financial services, maybe to help reduce the problem with fraud. Also IoT, and also cloud providers. Okay, so please let's move on. Yeah, okay, so for works, yeah, this particular, this is, anything you see here is actually binary, is not hierarchical. So that's just to show us that federated graph neural network model has been used for this DDoS attack, probe attacks. These are the literature that you can search to see how they implemented their model. But basically, all this work perform binary classification. Okay, so let's move on. Yeah, different type of attacks as well. That's the user to root, then the remote to local attacks. Yes, please. Just to show us the effectiveness of federated graph neural network. Okay, so what are the benefits of this? It helps with real-time detection. Then because it's federation, there is cross-organization intelligence, and there is privacy compliance due to differential privacy that was incorporated into the system. Okay, So there is an optimization referred to as, this is another work, this is not our work. There's a work referred to as FEDZIP, is an optimization mechanism in order to reduce the communication overhead. So they just try to bring up their results here. They also use federated graph neural network. And when they implemented their optimization, their communication optimization method, they discovered that, okay, before implementing their method, they had 700 seconds per rand. That means you have different rand when training your model. So for each rand, it took 700 seconds, 10 gig. That's the weight of the model updates that is being sent to the global cloud. Then high dropout rates. Then when they implemented their method, yes, so it's reduced to 16.8 from 700. Then also the model updates from 10 gig to 9.2 MB. Then scalable participant, that means it can accommodate more cloud. Okay, so yes. So basically now, if you want to bring this, whatever sector we're bringing it, be it finance, be it education, be it whatever it is, the first thing to understand is the basic privacy protocols. We don't want to send updates that will be intercepts, because there is also something we refer to as performance trade-off. So even with all of this, like I said, there are different security mechanisms that you can use. We have the differential privacy, we have the homomorphic encryption, and we have the secure aggregation. So we basically tested this differently on the model to see the performance. Okay, so when we did with the differential privacy, that is referred to as medium privacy, we got an accuracy of around 97%. But when we tested with homomorphic encryption, the accuracy reduced to 85. So we are now in between the choosing, do I want higher accuracy or I want higher privacy? Okay, so first thing to understand is the basic privacy protocol. Then whatever you're doing, you deploy first on a single cloud before federated cloud. Then also the performance baseline is look at existing models. There's a particular model we want to beat. Before, when you talk to detecting anomalies in the cloud, the first work that comes to your head is deep log file. But those works now, we've seen better models that outperform them. So we must have a model you're looking out to. Then we have the multivariate ensemble, whereby we have different model coming together to perform an output. Say, for example, we have different doctors with different specialty working on a particular patient. They are going to have a more robust diagnosis than having a single doctor just on that particular. So that's what the multivariant assembled. Then there is another thing I discovered, although I haven't, that's beyond the scope of this particular work, that I discovered when I was developing this model, is the issue of data imbalance. Because natural logs have high data imbalance. We can have, for example, let's say we have 100 million logs, for example. Out of that 100 million logs, we can have like 95 million normal data. The anomaly data will just be 5 million. So that is high data imbalance. And we know when it has to do with machine learning, with model, data imbalance is an issue. So that was a great issue. In fact, it took me more than 8 months to be able to do that, because existing data balance techniques that I saw in literature they were performed on flat classification, not the hierarchy that I was trying to bring into the system. So from literature, I discovered there is another mechanism that you can incorporate into that, although I didn't do that because I got another way to do that. And that is what is referred to as hyperbolic integration. So what they were trying to say is that no matter the work I'm doing, be it hierarchy, be it binary, whatsoever it is being done in Euclidean space. And there's going to be a lot of distortion because of the nature of the logs. But when you bring it to geometric space, that's the hyperbolic space, it's going to naturally cater for the data imbalance without you putting data balancing techniques into the model. So I think that's another thing to look at if you're looking at deploying this. Yes, cross-domain learning, then production handling, making sure the model you're building is robust enough, is scalable, and is secure. Yes, please, let's move on. Okay, yes, yes. So yeah, if this we have what we refer to as flower is an already made algorithm. Although this algorithm was built using flat space, but it is an already built algorithm for federated learning framework. Like you can just pick it up when writing your code. And we have the distributed graph library, which is very important when you're dealing with graph data because the graph is going to be large. Like for this particular work, I think I had like 66,000 nodes and edges about 3 million edges or something like that. So you can just try to visualize that the graph is going to be like. So we need that DGL library. Then the PyTorch geometry helps in that. Then the infrastructure, yes, you have to containerize your whatever you're doing. Then that's the Kafka is for stream processing because we're doing real time. It has to comes in. Then for this is just to harvest the log. This was what we use on our own to harvest logs. That's the object storage. Then yeah, please. Yeah, what you need, okay? Need machine learning experts, somebody that knows whatever machine learning approach they want to use. I've only been able to defend graph neural network. Maybe there is another one that can actually show relationship between data. Yes, we need that. Then you need security engineer because of that privacy protocol. Then DevOps engineer, product manager. Here's the infrastructure. I'm sorry for putting this 4 to 8. That was what we used, but definitely because of the this is dependent on the type of the data you're dealing with. Yes, so you cannot. I don't think you'll be dealing with 500 billion logs and then say you want to use 4 GPUs. I don't think so. But this was sufficient for what I did. Okay, so yeah, the network, then the storage. Yes, that is what is required. Please move on. Then feature vision. Okay, no, move on. Feature vision. Yes. Okay, no, please move on. Okay, so we want also another thing that we can incorporate into this work is what we refer to as natural language anomaly explanation. We want okay, like I said that the model is end to end. It picks in this natural language explanation will help with more features. So it's basically, we all know that our system understands zeros and ones, right? That's the language that we know the system understands. So our model, a lot of work was done to be able to extract necessary features from the logs. So, but if we have a model that can perform this natural language anomaly, I think it's going to help better than the it's not manual, it's still automatic feature extraction that we did. Then we should have automated feature engineering. Yes, we have that already. Then content aware detection. Okay. Yes, quantum computing. Yeah, that will take off then open challenges and opportunities. Yes. Okay. So another issue that we had with federated learning was convergence guarantee for non-IID data. So one of the challenges with federated learning is that we have non-independently identical data when it comes to federation. And when you train model on that type of data, it is slower and it might not even reach a convergence. So there should be an algorithm that you will use for convergence guarantee. For this, my model that was built, I use learning rate scheduling. I developed a custom loss function, and also incorporated FedPros into it to be able to cater for this non-IDD data. So different stuff. Then another thing, privacy bound for graph learning, then optimal compression theory. You can either use quantization, you can use pruning, or you can use knowledge distillation. Okay. Yeah, practical, we can have over 10,000 participants in a federation. We can have cross-domain generalization, then automated architecture search. That's when you have more than a lot of model that the system will automatically search for the right one to use for optimization purpose. Yes. Hybrid approaches. Yes, that is when we are trying to join graph neural network with another model now, maybe to add on to reduce the challenges that might come with graph neural network. Like I said, for the detection rate, we can see that it's between 85 to 99. So between that space that we have 85, that's 15. That is a lot. That means it did not detect a whole 15%, which is a whole lot. So I feel by the time we do hybrid, it will help the detection rate. Okay, yes, this can be, no, let's go back. Yeah, in financial service, this model can be used for real-time fraud detection, privacy compliance, collaboration. Yeah, and I don't think you'll be breaking any regulatory compliance with that. Then in healthcare, yes, it can be used for distributed patient monitoring, cross-hospital learning, then the complaints analytics, then the smart city. These are just applications of the federated graph neural network. It can be used for intelligent traffic management, energy grid, and all of that. So next step for researchers, like I mentioned, this domain of hyperbolic graph neural network is extremely new. So far in literature, what they've been able to do is the theoretical aspect of it. It has been used to build any model. So I feel it's something researchers can explore and see how they can bring that. Then also contribute to open source projects, then develop novel architecture. So that's just to explain the first point we have for the researcher. That's for the hyperbolic space. So basically, hierarchical data needs hyperbolic space. So it's going to help to reduce the exponential distortion that we have with existing method, then the high dimension needed, then poor hierarchy preservation. Because to incorporate hierarchical classification into this model, it's practically involve me, first of all, manually defining the hierarchy myself. But I feel if we incorporate hyperbolic into it, it will automatically determine the hierarchy itself. So yes, that's the problem we have with existing model. Yes, okay, the benefits of hyperbolic graph neural network, exponential capacity, natural hierarchy, then efficiency. From literature, it was said, although they did not perform it, but they just said it will have. Therefore, practitioners start with small projects, prototypes, small ones, then build internal expertise, collaborate across organizations. Yes, please. Then for organization, please invest in privacy, preserving technology, partner for federated initiative. Federation is the new goal. It's amazing. Lead in responsible AI. Then remember this point. So from all of the story, please remember that whatsoever you're doing, in as much as we want high performance, we want the privacy. We want the privacy to be intact, yes. Also, the communication, like sending the global updates to the global server, yes. From literature, we discovered that major cloud providers are actually looking into federation now. Then real deployments already showing results, although we do not know the architecture that they use, but from literature, we gather that we have cloud provider coming into federation, yes. Okay, we're going to have definitely competitive advantage when we collaborate, when we form federation, rather than being alone. Then, in order to read more on everything that I've said, I picked out just 9 papers, recent papers, I think from 2023. Yes, they should be from 2023. Yes, to 2025, in case you just want to read more on this. Then, yes, questions and discussion. Thank you.
You mentioned different types of encryption, right? Maybe this one performs better. Or in terms of communication optimization, you said there are different algorithms. Yeah. So is there any work out there that compares all these algorithms or all these encryption and say, okay, this is better or that is better for implementation?
Okay, yeah. No. To the best of my knowledge, no. But what I did with my work, like I said, I use differential privacy. I use differential privacy for my work, and that was what I got with those accuracy.
Numbers.
Yes. So I use another thing I did was to use I'll call it a simple homomorphic, because it's not, that's another person's work. She's also in our research. She's presently working on homomorphic encryption. I just use like just few of it to see. Then I discovered maybe because I didn't use the full homomorphic, but I discovered the accuracy dropped a whole lot. That was when I mentioned performance and accuracy. So because homomorphic encryption is full privacy, it involves a lot. It's another PhD work on itself. It involves a lot. So, but when I just use like a baseline of it, the accuracy dropped. Yes. So that is, but presently in literature, there is no work that actually compares like in federated. No, not to the best of my knowledge, sir.
All right, thank you.
I have a question from online. It's a couple of questions.
Given the critical need for explainability in fraud detection, e.g. justifying why a customer was blocked to the regulator, how can we ensure that deep learning models remain interpretable? Okay. Specifically, I think that's one question.
Okay.
I think you mentioned you did quantization, right? From 32-bit to 6-bit for some of the
From
features.
32-bit to 8-bit.
To 8-bit, yeah, sorry. I think it's trying to ask the loss, right? So, because you said there's no loss for me, I don't believe it.
No, there is no loss.
There'll be loss, and with loss, you lose explainability or you would lose some data. So how are you still able to make the system explainable?
Okay, so when you talk about explainability, I think that's the hierarchy explains it. Let me explain what I mean by hierarchy. Okay, so we are building a system that does not just detect anomaly. So the first level of the classification is the detection. So it detects there is an anomaly. Then there is another level. It detects the type of anomaly. Okay, is it error? Is it fraud? Is it whatever it is? Then there is another level that now classify the type of error that it is and the type of fraud. Is it fraudulent transfer? Is it fraudulent withdrawal? Whatever it is. And I think that is explainable enough, right? Though it doesn't stop. Like for the model I built, it has 5 levels. With the logs I use in building the model, what it does first is detect anomaly, because this is for what's it called, our cloud. So it detects anomaly. Then the second level is the type of anomaly. Is it error anomaly? Is it warning anomaly? Because different type of anomaly calls for different action. If you have warning anomaly, you don't have to be scared. It just means that, okay, something it might be wrong. But if you have critical anomaly, you have to run because the system is about to fail. If you have error anomaly, you can still drag yourself to it. So that is why we must know the type of anomaly that occurs. Then it doesn't stop there. It goes on to the application that produced that anomaly. So we want to know, even if it is error anomaly, what type of cloud application is producing that? Is it computing? Is it messaging? Is it networking? Then it doesn't stop there. It goes to the specific module that produced that anomaly. So I think that is giving an... if I get the question
I'll
right.
also argue, but I'll say it did not say why. It just helped me identify what, but it did not say why that.
Why the anomaly is coming from.
Yes.
Even with a specific module.
Yeah, it just tells me a module has an anomaly. I don't know why.
We don't know why it has the...
With your description, though, I don't know why.
Yes, because that's what the model basically does. It just break it down to the specific module. That so I think, yeah, we can now start looking at the why. But you as a cloud administrator, if the model is doing the why for you, so that's going to take your job.
But if I use this algorithm for fraud, it would be nice to know why.
Okay, for fraud now.
Yes, for example, is it for fraud? It would be nice to know why, right? Like, so for
and okay, so let me get let me get something right there. You know, like I said, this particular model was built for performance anomaly.
Say that again, please.
For performance anomaly, you know, I stated earlier that we have security anomalies, then we have... So I think for that fraud will involve both security and performance, right?
I don't know. Fraud...
You are in...
I do fraud, but I don't know whether when you say security and performance, what do you mean? I don't know.
So when I say performance, I mean the components that are involved. So it can be like maybe a failed...
So if I want to do fraud, I might not probably want to do it from logs, right? I would want to do it from my actions, right? A series of, build a graph for my actions and the entity involved in my actions.
Your actions are logs.
No, I agreed. I agreed. Okay. I agreed.
Yeah.
So when you're explaining the whole federation stuff now, you talked about local and global. So the local will sit in different cloud, right? Different cloud system. Am I correct?
Yeah, finish.
So the global, where is it going to sit? Is it, because it feels to me like the local should be like in the different clouds, right?
Yeah.
All communicating to the global.
Yes.
And then where would the global actually sit? Is it going to be on its own cloud, or is it going to be what exactly? Where is it going to sit? I don't know if you understand the question.
Yes, I do. So the global can sit anywhere. So let me explain this. We have different cloud providers that want to form a federation. So we're picking one to be global for global coordination. That's just it. So it can be anywhere. But the thing is that they are going to align to the rule that govern the federation. So we can decide, okay, is this particular cloud provider that is going to be the global coordination, and everything that has to do with global coordination will be deployed on that cloud. So it has to be happening. For this particular one that I worked with, the global coordination is in covenants. So it doesn't have to. It can be anywhere. There's another question. Please, what was it?
Yes, online. Yes, there is another question online from Babatunde as well.
Okay.
He said, was there a comparative analysis of training the graph with classical ML model as well?
I did not get that, please.
I think he's trying to ask, did
I compare? Yes, I did. I did with a whole lot of work. So I did basically like 2 different types. Number one, I compare with existing work that did anomaly detection in cloud. I did that. Then I did with centralized approach, that's on a single cloud. With decentralized approach, that's on federated. Then I did with flat model. Then I did with hierarchical model. So basically, I don't have it here. I'll show you. So basically, what I did was, okay. Another thing that this model does is that what's that name again? There is a name to it. I'll say when I remember. Okay, so it takes the model from the global cloud now to train its own, but it doesn't train it word to word. It's as a way of tweaking the model to suit its own data. That was what helped to solve the challenge with non-IDD data. I don't know if you're getting what I'm trying to say now. So we have a model. Let's say this model was built with 5 parameters. Then one of the parameters is I set the learning rates, for example, to be, although I use learning rate scheduling, but let's take, for example, let's say the learning rate was set to 0.001. And on this particular model, it gave 99% accuracy. If it's deploying another model, because of the type of data that is there, that learning rate might not work for that data. It might give a lower accuracy. So what the model does, well, part of the intelligence that is built into the model is that it has a way of tweaking, and it's not necessarily going to deviate so much from the model update. So the model was built with graph neural network. When it gets to another cloud, it doesn't mean that it will change to LSTM. It will still use the same, but try to tweak it to suit its own data. Yes, please.
You're saying you did not have to manually tune hyperparameters of the model.
Yes, no,
so
yeah.
The model is able to tune its own.
Yes, based on the data. On the data that it's so that was yes, I compare with that, and this particular one gave better accuracy, I think. Continue. I want to give you the right figure. So it gave 15.7% accuracy improvement.
I don't know how to do this.